Where does speed come from when an object falls? How can height become motion? And is there a way to connect these quantities to the work done by a force? These questions lead us to one of the most abstract yet powerful concepts in physics: energy. Energy is one of the most useful ideas in all of science because it allows us to describe an enormous number of physical phenomena using the same language. In this first part, we will focus on work, kinetic energy, and a powerful theorem that connects these ideas. Later in the series, we will come back to height, potential energy, and conservation. For now, we will leave aside the modern and relativistic meanings of energy and build the concept from the simplest physical situations. Before starting the main discussion, we need to introduce one key idea that will be useful later: work. In physics, work is another abstract concept, but it gives us a precise way to describe how energy is transferred by a force. In this video, we will denote work with the letter L. When a force acts on an object and the object moves, that force can do work. In the simplest case, work is defined as L equals F dot delta S. Here, F is the force, and delta S is the displacement of the object. Both force and displacement are vectors, so this is not an ordinary multiplication. It is an operation called the dot product. The dot product tells us how much two vectors point in the same direction. Mathematically, writing F dot delta S is equivalent to writing F times delta S times cosine theta, where theta is the angle between the force and the displacement. This angle is the key. If the force and the displacement point in the same direction, then theta is equal to 0. The cosine of 0 is 1, so the work is maximum. This is what happens when we push an object in the same direction in which it moves. The force is helping the motion. But if the force is perpendicular to the displacement, then theta is equal to 90 degrees. The cosine of 90 degrees is 0, so the work is 0. This may sound strange at first, but it also makes sense visually. If an object moves horizontally, but the force points vertically, then that force is not helping the object move along its path, so it does no work along that displacement. In general, the more the force points in the same direction as the displacement, the more effective that force is at doing work. But keep in mind that even though F and delta S are vectors, the result of a dot product is always a number, not another vector. So work has no direction. L is a scalar quantity. Finally, the unit of work is the Newton times the meter. This unit is called the joule. And this is important because energy is measured in joules too. So work is one of the ways energy can be transferred into or out of a system. This point will become clearer later. Now let us move to kinetic energy. Kinetic energy is the energy associated with the motion of an object. In physics, a body can move in many different ways. But for now, we will focus on the simplest one: translation. That means ordinary motion from one place to another. Kinetic energy is defined as K equals 1/2 mv squared. Here, m is the mass of the object and v is its speed. So kinetic energy depends on both mass and speed. But there is an important detail. The speed is squared. This means that speed affects kinetic energy more strongly than mass does. For example, if the speed doubles, the kinetic energy does not double. It becomes 4 times larger. This is why fast-moving objects can carry a lot of energy. Even a moderate increase in speed can produce a much larger increase in kinetic energy. But there is another very interesting way to understand kinetic energy. It comes from a result called the work-energy theorem. This theorem says that the total work done on a body is equal to the change in its kinetic energy. Using our notation, L total equals delta K, or more explicitly, L total equals K final minus K initial. So the total work done on the object tells us how much its kinetic energy changes. To understand why this is true, we will use a little more mathematics, but nothing will be left unexplained. To keep the idea as simple as possible, let us consider the case where the force and the displacement are parallel. In this case, the work is easier to write. Instead of looking at the work done over a finite displacement delta S, we look at a very small displacement. This is a common idea in physics. A very small displacement is called an infinitesimal displacement, and instead of writing delta S, we write ds. If the displacement is infinitesimal, then the work done is infinitesimal too, so we write dl equals f ds. Now we recall another basic idea from physics. Position, velocity, and acceleration are deeply connected. Velocity describes how position changes in time. Acceleration describes how velocity changes in time. Mathematically, these ideas are written as a equals dv over dt and v equals ds over dt. The symbol d over dt is a mathematical operator called a derivative. It measures how a quantity changes instantaneously with respect to time. So dv over dt means the instantaneous change of velocity with respect to time, and ds over dt means the instantaneous change of position with respect to time. Now let us go back to the work formula. We have dl equals f ds. From Newton's second law, we know that F equals ma, so we can write dl equals ma ds. Now we substitute the acceleration a equals dv over dt. So dl equals m times dv over dt times ds. But from the definition of velocity, v equals ds over dt. This means that ds equals v dt. So we substitute ds with v dt. Then we get dl equals m times dv over dt times v dt. Now the dt cancels out, so we obtain dl equals mv dv. This is the key step. The small amount of work done on the object is connected to a small change in its velocity. Now, to find the total work, we have to add all these infinitesimal contributions. Mathematically, this is done with an integral. An integral is the inverse operation of a derivative, and it is also often used to calculate the area under a curve. This idea fits very naturally here, because work can be interpreted as an area under a force displacement graph. So we integrate both sides. On the left, the integral of dl becomes the total work, L total. On the right, we integrate mv dv from the initial velocity to the final velocity. So we obtain L total equals the integral from v initial to v final of mv dv. Since m is constant, it can be taken outside the integral. The integral of v dv is 1/2 v squared. So we get L total equals 1/2 mv squared, evaluated between the initial velocity and the final velocity. This means L total equals 1/2 mv final squared minus 1/2 mv initial squared. But this quantity is exactly the change in kinetic energy, because kinetic energy is defined as K equals 1/2 mv squared. So 1/2 mv final squared is the final kinetic energy, and 1/2 mv initial squared is the initial kinetic energy. Therefore, L total equals K final minus K initial, and this is L total equals delta K. This completes the demonstration. The result tells us something very important. Work is not just a formula involving force and displacement. Work measures how the kinetic energy of a body changes. If the total work is positive, the kinetic energy increases. If the total work is negative, the kinetic energy decreases. If the total work is zero, the kinetic energy stays the same. So when a force does work on a body, it can change the energy associated with its motion. But this naturally raises a deeper question. If kinetic energy increases, where does that energy come from? And if kinetic energy decreases, where does the lost energy go? In the next video about energy, we will see that in many physical systems, the answer lies in the counterpart of kinetic energy, potential energy. If you enjoyed this video, consider subscribing to the channel and leaving a like. Thanks for watching, and I will see you in the next video.